Welcome back, folks. In the first half of this week, you've gotten a really good sense, I hope, of how to build organic structures and then how to alter them to actually take organic molecules and put them through our first real chemical reactions. What we're going to spend the rest of this week doing is first reviewing those reactions and seeing what those opposite reactions actually look like and how they're carried out. Then we're going to really dive into this idea of functional groups, these specific, repeated, very common arrangements of atoms that allow for certain reactions to take place and others not to. Lastly, we're going to spend some time getting to know the IUPAC, that is the International Union of Pure and Applied Chemistry's system for naming organic molecules, because as these things get more and more complicated, these are very hard to just point at and rattle off a chemical formula for. The structure, as we've already seen, is going to matter a little bit, and so we want to be able to say in very quick terms what that structure actually is. Let's get things started with a little bit of review of the reactions you saw earlier in lab. So to start things off, if you go to the top of the first page for our Week 6 video lecture worksheets, you'll see a little fill in the blank here on addition reactions, which was the first major type of reaction we looked at in the lab workshop. I'd like you to pause the video and take a moment to try to fill in these blanks and see what you remember from that. Take a moment, and when you're ready, we'll come right on back. Okay, now that you've taken your moment, recall here that when we did addition across an alkene, and this was a group that has a very well-defined tendency to undergo these sorts of reactions, we turned the double bond, we turned this group of 4 electrons right here, into just 2 electrons and what we term a single bond. And in doing so, we repurposed 2 of the electrons that were making half of that bond to make new bonds. And so we use those electrons to make new bonds or new attachments to 2 halves of a small molecule. And we specifically looked at 2 small molecules here. We looked at the HOH, the water molecule here, that would split this way and kind of asymmetrically. We also looked at H2, which would be H and H, and in that case we would split that in half and add a hydrogen to each side. We had different names for these depending on what it was that we were adding. So when we did add water, H2O, HOH, we called it hydration. Just like when you add water to yourself, you get hydrated. In that case, we had to be a little mindful of where the OH went. Remember, the OH went to what was the carbocation, what was the positively charged carbon, and we said that happened at the more substituted carbon. In other words, the carbon that had more carbons bound to it out of the 2 that were in the original double bond. And of course, if the added molecule was H2, it was substantially easier. We basically just erased the double bond, and we would understand from that there were now hydrogens on either side. We called that reaction hydrogenation. And when you're looking at these words, it's very important to look at that and to try to ignore the hydra part, because that's the same on both of them, so it's not going to help you tell the difference. Look for the ogen. You see that? It's hydrogenation. It's H2. You don't see it, it's hydration. You've added water. So reminding ourselves of what these reactions kind of looked like, if I took something like, for instance, this molecule, and I looked to hydrate it by adding a water molecule, what I would do here is I would again take the H and the OH and I would add them to either side. And I would have 2 possibilities when I do that. One would be that I could put the OH on this carbon, the one that was on the left side of the double bond originally. I could also put the OH on this side instead. Remind yourself, if I do it there, then I won't have it here, because this will be where my H went. However, putting the OH here would be putting the OH at the less substituted carbon. Notice this carbon only has 2 C's connected to it. This carbon over here has 3. 1, 2, and 3. So this wins out. This would be my major product. On the other hand, if I simply hydrogenated this molecule, the result would look a lot more boring. Notice that I would just wind up with that particular structure. Now, of course, the thing to bear in mind is that when we're doing this, we're not just adding OH right here. Remember, we're adding an H at that position that wasn't here beforehand, because this originally had just a single hydrogen. Now, it's got 2, and so one of those is a bonus hydrogen. Similarly here, this carbon, can't see it, that carbon in the initial structure has no hydrogens on it. I can already see 4 bonds, 1, 2, 3, 4. This one's got 3, so that would have 1 hydrogen attached because it's got 3 bonds shown explicitly. Once we're done with it, there's now an H here, and there's now 2 H's here. And so you might say that those hydrogens have been added to the structure. In addition, we saw one other kind of double bond that can be hydrogenated. Not hydrated, but specifically hydrogenated. And that was the CO double bond, what we termed a carbonyl. When we start talking about functional groups, you'll see that this is not technically a functional group because carbonyls are everywhere in organic chemistry, so you have to look a little further. But the carbonyl group in the right situation can be hydrogenated. And when that happens, it's a similar sort of idea. We peeled off the double bond, we added H's to both sides. And so if I put an H here and an H there and I get rid of my double bond, the result is that. Which actually is a functional group we'll learn to call an alcohol. Remember, in this case, the H that's attached to this carbon doesn't have to be shown explicitly, because CH bonds are generally completely left out of these sorts of structures. On the other hand, the H attached to the O does need to be shown explicitly. OH bonds are not left out. Now, the other major class of reactions we discussed were hydrolysis reactions. And just as a reminder here, just a couple blanks to fill in. What do hydro and lysis mean? Okay, hope you paused the video there and came up with this. So hydro means we added water. So this will be kind of a variation on a hydration reaction. But lysis means specifically that we are going to break a bond. Lysis, it turns out, is a very commonly used word to mean breaking something. It gets used a lot with breaking cells. There's a process that can happen when you administer an incorrect solution into an IV that's called hemolysis. In other words, breaking of blood, which you can imagine is probably not a great thing. Similarly, the process that is undergone to deliberately break red blood cells when you're trying to isolate other parts of donated blood is referred to frequently as hypotonic lysis. So get used to that little bit right there. The great thing about scientific words is if you know the pieces, you can start to piece together what big ones mean. Now, the big difference with hydrolysis was that we did it across a single bond. And when we did that, the downgrade was from single to nothing. And that meant we actually broke a molecule in half in the process. So again, examples of that. We did it with, for instance, an amide. So if we had a molecule like this, and remember this group right here, the carbonyl with a nitrogen bound to it, was referred to as an amide. We also saw in the workshop that something called an ester, where that N is replaced with an oxygen, could also undergo this. In these cases, what we did when we broke the bond is we broke the one between the carbonyl carbon and the electronegative atom that was single bound to it. And so it would be this one, or in the case of the ester, it would be between the carbonyl and the single bound O that would be in that spot. When this happened, again, we're going to take the pieces, and just as we did with the addition reaction, we're going to need to add H to one side and OH to the other. This time you didn't have to look at carbocations, you just kind of thought about this in terms of electronegativity. The more positive side of this broken bond would be the carbon in the carbonyl. In fact, it's being starved of electrons by the O. And then the nitrogen over here would be the negative side. So if I'm thinking about the water as having a negative OH and a positive H, they're going to match up where they're wanted. So the OH will go here, the H will go there, and these will be my two individual products. We get two separate molecules now. This functional group we'll learn eventually to call an amine, and this one over here will be called a carboxylic acid. Again, that being this group right there.